So I want to show you a quick example of what I mean by output compression. So the point here is that almost no matter how you work with Maple, you're going to generate a lot of data, and usually it's going to be a challenge to find the interesting parts of this data. So unless you're really lucky, it's going to be necessary to look at what your experiment outputs and then somehow try to cut it down in size so that you can understand what is interesting about the data that you get. And the little example I want to show you, it's also in the book, is to look at what happens when you factor the so-called cyclotomic polynomials. So I'm looking at the polynomial of the form x to the n minus 1, and then I'm asking Maple to factorize that over the integers. So that means that I can write it out into smaller polynomials, but you can see I'm only allowed to use integer coefficients when I make this factorization. So of course we know that we can factorize further if we were allowing ourselves to use complex numbers, but we're not doing that here. Right, so I've done this with the first one, so that is just x minus 1, so nothing happens there. The next time it's x squared minus 1, which we all know is x minus 1 times x plus 1. And then you can sort of keep on going. You can see you always have x minus 1 as a factor because 1 is the root of x to the n minus 1, of course. Sometimes that's all that happens, and sometimes you can go further. But there's a clear pattern that comes out when I've done this experiment 9 times, and that is that the coefficients that I encounter are all plus or minus 1, or 0, of course. Right? So what happens here is that when we do this experiment, we're led to the interesting observation that we never encounter any coefficients except for plus and minus 1. And that's not given by the way that we've defined it, so that would be an interesting mathematical observation if it was true. So how can we figure out if this is true? Well, we can sort of try to go a little bit further. And of course, to help ourselves, we might want to put things in a, a vertical list like this, so that instead of looking at these comma-separated data, we have them one line at a time. But the thing is, of course, and so that usually that's a little bit easier to read. And you can see I can very easily do this by passing from using sequence to using for, because the for loop will automatically insert a new line at the end of every iteration of the for loop. There's a little thing here that I would like to point out. You can see that I'm using m here and not n. And that's because when you've run a for loop, the m will end up being set to the last entry. And so when I've now run this for loop, m equals 9. And of course, then when I go on, if I had done this with n, then the next time I did this computation, Maple would say, well, n is 9, so why are we talking about the sequence from 9 equals 1 to 9? That makes no sense, and it would complain. So that's another difference between using sequence and using for loops, is that it will actually define the loop variable at the end. That's not happening with n inside the sequence. So that's another distinction. But really what I'm after here is that suppose I do this up to like 150. I mean, I can very easily do this. It doesn't take very long time, and it gives me screenfuls of data, all of which look very promising, right? So you can see all the entries I have here. They all look like they're plus or minus 1. It's not that there's lots of 2s and 3s and 4s and so on. So that seems to corroborate the theory that they're all like this. But of course, it's really hard to tell when you have the data like this. So I want to somehow compress it so that it's easier for me to see what's going on. And this is the point that I'm trying to make. So how can we compress it? Well, there's various things that are built into Maple. One is coeffs. So coeffs takes a polynomial and extracts the coefficients. So you can see it works the following way. You take a polynomial. This is like the x to the 4 minus x to the 3 plus x to the 2 minus x plus 1. And then it just strips off the x's and makes a list of the coefficients that you encounter. Right, so in this case, I would get 5 numbers, and they're all plus or minus 1, by the way. I have to say x here. That just means which variable I'm doing this relative to. So, maybe this had some had some a's or b's in it. That would then be fine for that. And I can compress it in a very simple-minded way, just like this, by taking these 5 data points and put them inside curly brackets. This means I'm making the set, right? So I'm making the set with plus and minus 1 in it. So I will get rid of the repetitions in a very easy way by putting things inside the set. But the problem, of course, is that that's not what I have here. I don't have a simple-minded polynomial like this. It's something that is a result of a factorization. So something like this here, which is for 150. You can see it's a product of a lot of polynomials. And then you have to wonder how you can sort of look at them individually so you can get the correct information out. And this would take a little bit of time. First time I did this, I had to think about this a little bit. And I went into the help system, and there's really nothing here that is helpful. But you can see over here, there's something called factors. So the original version that I used called factor, and that this actually happens quite a lot in Maple. There's a version that sort of outputs the information of the factorization not as a product of the polynomials, but as a list of polynomials. So the way it works, and you can sort of see it explained here, but suppose you want to do the factors of x to the 4 minus 4. Well, that is the product of x squared minus 2 times x squared plus 2. And then you have a number 1 here and a number 1 here, which is the multiplicity. So if you had a repeated term, then it would come with a 2 or 3 and so on, like it does here. If you factor this quadratic here, this is 3 times x plus 1 squared. So you get 3 out because that's the coefficient in front of the leading term. And then you have here x plus 1 twice. Right, so essentially, if you look carefully at this, you can see that what it does, it will take something like this, which by definition it will have a 1 at the very top of the factorization, so I don't have to worry about that. But the other terms, you can see now I have these individual polynomials with a weight on it, and that weight is usually 1. So what I can do is I can say, okay, now for instance we've looked at x to the 10 minus 1. I've done this factorization, and now essentially I want Maple to look at the coefficients of the terms in these polynomials. So what I will do is, first of all, I throw away this 1 that I've highlighted up here by taking just the second term of factors. Right? So what I'm doing here is if I only take the second term, that throws away the first term. That was the one that I was interested in. And now I also have these 1s or possibly 2s and 3s telling me the multiplicity that these terms come with. That's also redundant. So I will get rid of this by mapping. So this is a construct that's very useful. So let me explain how this works. So I take this list of factors and I'm, oops, I have to do this wrong, like this. So the way this works is that I apply the map that sends x to the first entry of x to the result of the first computation I did. So originally they were pairs with a polynomial and a weight, and now I've just extracted the first element of that pair. That's what this does. So you can see this extracts this as my polynomials, and now I can just apply coefs to it, so like this, and you see all that I now have is a collection of all this data. So essentially what happened was, if I remove this convert, which was put on at the end, so what happens was that I took the first polynomials, I looked at the coefficients that I encounter, they were all 1, so I have a 1. Oops, a 1, like this. Then I took my second polynomial, this one, and I took the coefficients that came out. They were plus and minus 1, so I have them down here. And I keep on doing this. And then in order to get rid of the repetitions, I first I had these two ones, they are here. Then I have the 1, minus 1, 1, and so on. I have them here, and so on. And now to get rid of the repetitions, I convert this into a set. And now to a set like this. And that gives me 1 plus and minus 1, so you can make sure that this actually satisfies the conjecture that I'm trying to make. And now it's really easy to do this computation all the way up to 150. I'm printing them out one at a time, and you can see that this is now a lot more systematic. And when I browse down, I'm very easily alerted to the fact that something new happens here at 105. So at 105, there's actually a minus 2. And it's very easy to see because you can even see that the list is sort of expanded to make room for the minus 2. So, very easily you can see this data that there's something interesting going on at 105, which didn't happen the other places. So compressing the data helps me a lot in seeing this, right? And you can even see, if you were to take 105 and factor that, I'll just show you what that looks like. So factor x to the 105 minus 1, like this. Don't know what that's supposed to be. Then, sure enough, there is a 2, but where is it? Here, right? So even if you know it's there, it's sort of difficult to find. So you see, this is it's very important in order to understand what's going on, to have an efficient way of dealing with the data. And now, of course, you could do this even further. You might say, for instance, I want to go through the numbers from 150. Just tell me the ones that have more than 2 numbers occurring in their factorization. And this is the one it prints out 105. I did 2 things. I put in an if clause to only print something if there was more than 2 elements in the list of coefficients. And I did something else. I put in a colon here at the end rather than a semicolon. Because if there's a colon at the end of the for loop, it will only print something if there is a print command, right? So that's to suppress all the non-interesting information for other numbers than 150. And the point is now I can do this pretty far, right? I can ask for what are the numbers where there's more than 1, and I can get a list, and I can analyze that and get closer to understanding this problem.